Okay, so the very first one on the practice problem says the following. It says, when a beam of light originally traveling in air enters a piece of glass having an index of refraction of 1.5, its frequency does what? So, light going from air to glass. Let's draw a little picture of this thing. Here's our chunk of glass. Here comes our light wave. And it's going to head into the glass, and something's going to happen to it. Okay? What happens to this light wave? Well, when it's in air, we know that it is traveling at c. But when it's in the material, what's it traveling at? V, which is less than c. Right? V equals c over n. C we know is lambda naught times frequency naught over n. But now in this material, it's going to be some new lambda times f. And so now you're faced with a choice, right? Is lambda equal to lambda naught over n, or is f equal to f naught over n? One of those is true and one of those is false. And this is what this question is asking about. It's asking, is this one true, or is the frequency not affected? So anybody remember which one is affected and which one is not? The wavelength is the one that's affected. Okay? The wavelength gets shorter, and so if we draw this in the material, we should really draw it with a shorter wavelength. Okay, propagating through the material, but it still has the exact same frequency. So we would say that the frequency is, in fact, unaffected. All right, and as we go through these, just shout out if you have questions or comments or want to think about extensions of the problem. That's fine. All right, let's take a look at number 2. Number 2 is talking about a single-slit diffraction problem. And it says the following: a single-slit diffraction pattern is formed on a distant screen. Assuming the angles involved are small, by what factor will the width of the central bright spot on the screen change if the slit width is doubled? So let's think about this for a second. We've got a hole in a screen. Here comes our plane wave. We know that it's going to do this sort of thing, but there is also a little bit of interference from the edges, and the resultant pattern looks like this. Okay? We have some equations that tell us about the dark spot right there and that angle of the dark spot relative to the optic axis theta. Now, we might be able to make some sense of this without even looking at those equations. Okay? And the way I think we should try to make sense of this is the following. Let's say I do this experiment again, okay, but I use a very, very small hole in the screen. Okay. The single slit is now small compared to this one. When I draw this diffraction pattern on the screen over here, Yeah. Okay. That would be Joe. Failing to pay attention to what's happening up here. Come on, Joe. Keep up. Thank you. All right, so when I go through a much smaller hole, is that diffraction pattern going to look like this? Is it going to look squished together? Or is it going to look expanded out? What do you guys think? Okay, it's in fact going to expand out even more. Okay, and this is the weird thing about diffraction. Diffraction means if you go through a small hole, you're going to spread out much more. If you go through a big hole, you're going to spread out much less. And so in fact, the diffraction pattern is going to do this. Okay, it gets much wider over here. All right, so with that information, let's see if we can make some sense of the answers. It wants to know what factor will the width of the central bright spot. That's this thing right here. This is the central bright spot. Okay. And it says what factor will that change if the hole in the screen is doubled. So if we go from this to something like this, what happens? Well, what we said is it's a big wide pattern with a small hole. It's a little bit narrow with a larger hole. And so it will definitely have to be cut down. And the only two options for cutting it down are B or D. B says it will be cut to 1/4 its original size. D says it will be cut in half. And so at this point, we have to think, are there any squares in that equation? Right? When we talked about the single-slit diffraction equation, were there any squares anywhere? Was anything raised to the 2? Or was it all just linear?
Siri not available.
Well, I wasn't asking Siri, but it's good to know that she's unavailable. It's all linear, right? Because it looked like d sine theta equals m lambda, right? Maybe that's the double slit equation, but we have something very similar for the single slit equation. There's no squares anywhere. And so it has to be linear, and so you say d, it will be cut in half. Okay, number 3, let's take a look at that one. So number 3 looks slightly redundant. It's very much related to number 1. It says when light travels from air into water, what changes? Okay, so I don't think we need to belabor this point. We already know that its velocity changes, but we know that the frequency stays the same, therefore the wavelength changes. So if you look at all the different options, the only one that fits that bill is A, its velocity and wavelength change, but its frequency does not change. All right, so let's move on to number 4. 4 is a polarizer question. And it says an ideal polarizer with its transmission axis rotated to 30 degrees relative to the vertical is placed in a beam of unpolarized light of intensity 10 watts per square meter. After passing through the polarizer, what is the intensity of the beam? So, unpolarized light is like sunlight. And now we're going to send that sunlight through a polarizer. So remember, we were drawing our polarizers like circles with an arrow to indicate the transmission axis. And it says that it is 30 degrees relative to the vertical. They want to know how much is coming through the other side. So if this is the intensity of the sunlight coming in, we want to know I on the other side of this polarizer. So how should I approach this problem? Somebody give me a thought. Eudora, I see you hiding back there. What should I do for this problem?
You can use Malice's law.
Okay. We can maybe use Malice's law. All right, what is Malice's law? Let's talk about Malice's law for a second. Malice's law says the intensity coming out is I naught cosine squared of theta. Okay? And when we talked about this in class, we drew the following picture. We said, oh, here's our sunlight. There is some intensity of the sunlight coming in. I'm going to put my first polarizer up, and that means there is I naught coming through that polarizer. And I'm going to draw the second polarizer at an angle theta. And if I want to know how much is coming through, then Malice's law holds. I equals I naught cosine squared theta. Okay, this is the one that we did in class. But that looks a little different than this, doesn't it, Eudora? Because here, we only have one polarizer. Whereas in Malice's law, we drew it with two polarizers. So what's the purpose of that first polarizer in this picture? What's the purpose of this polarizer?
To direct, to only let through one direction of light.
Exactly, to only let through vertical polarization, okay? That's not what this arrow is indicating, so let's draw it with a dashed line. This is the continuation of the beam, all right? Keeps going through. And if I think about the polarization that came through after this first polarizer, it's vertical. That's what that arrow represents. Okay, and that's what we called I naught. And now when you go through the second polarizer, how much goes through the second polarizer? It is I naught times cosine squared of theta. But how much of I sun gets through that first polarizer to I naught? Do you remember what we did in class? There's some factor that I need to include here. Is it all of I sun that came through? Or is it some fraction of I sun that came through? Well, I sun is unpolarized. Okay? It has a polarization like this, going up and down, but it also has a polarization like this, going into and out of the board. This guy only picks out one of those. It picks out the vertical, it eliminates the horizontal. So what factor should I put here? A half. It's going to pick out half of the light, right? Since this is vertical, that's half of the light. The other one, horizontal, gets extinguished at that first polarizer. All right, so that looks pretty close to this, except our polarizer is not vertical anymore, right? It's off at this angle, 30 degrees. And so the question is, does that matter at all? If I hold up a polarizer and I look at the sun, which you should never do, of course, because it's a little bright. Even if you cut it down with a polarizer, it's still very bright. But let's say you do that. Let's say you look up at the sun with your polarizer, with your polarized sunglasses, and now you turn your head sideways. Does the sun get any dimmer? No, it doesn't, because it is unpolarized. Okay? It doesn't have any particular polarization. It has a combination of vertical and horizontal, and you can combine those to make everything in between. So this is in fact exactly the same as this. Okay, because if I rotated my sun by 30 degrees, it's going to look exactly the same as this problem over here. So what's the intensity? It's I sun over 2. And they told us what I sun was. It was 10 watts per square meter. So we're just going to divide that by 2 and we get 5 watts per square meter. Okay, which is one of the answers there, answer A. Okay, so that one's a little bit tricky because you see that theta and you think, oh, I immediately need to go to Malice's law. But once you drew it out, you probably recognize that it wasn't quite the same as when we talked about Malice's law. If there's questions as we go, just shout them out. And what's your name? Miranda? Miranda? Miranda is monitoring the online environment, I hope, unless you're checking your Facebook page. I don't know what's going on over there, but if there's any questions.
He just, I don't know who, asked to do number 10.
Okay. Well, that's kind of jumping ahead, but we'll get there. I was thinking we'd just go through them all unless you guys are bored and don't want to do that. That's okay? Yeah? They're hungry. They're hungry for knowledge. That's what I'm going to go with. Hungry for physics knowledge. That's my takeaway message here. Okay, so let's look at number 5. And number 5 says, in a double slit experiment, the slit separation is 2 millimeters, 2 wavelengths, 750 and 900 nanometers. Illuminate the slits. A screen is placed 2 meters from the slits. At what distance from the central maximum on the screen will a bright fringe from one pattern first coincide with a bright fringe from the other? Interesting question. Okay, so this is a double slit experiment, but we have 2 different colors. Okay, so we're going to draw this hopefully carefully. Okay, here's our double slit. Here is our distant screen. And now we're going to send in 2 different colors. And we're going to pick red and blue, even though those colors are red and near infrared. Okay. So blue light coming in, red light coming in. Those are both plane waves. They illuminate both slits. And there is going to be a diffraction pattern over here. And when we think about the 2 wavelengths, and we can label them, blue is going to be 750 nanometers, red is 900 nanometers. Again, these don't correspond to the actual colors, right? 750 is at the red end of the spectrum, and 900 is at the near infrared end of the spectrum. But what do we know? Well, if we go in with shorter wavelength light, blue light, we know that it's going to make some diffraction pattern over here, okay? And we kind of know what that pattern looks like. It looks like this. Okay, you have these bright regions and you have these dark regions. And now if I go in with red light, am I going to see the exact same thing, or am I going to see something different? Well, let's go back to the equation for a second for 2 slits. The equation for finding the 2 slit maxima is d sine theta equals m lambda. D is this distance between the slits. Theta is this. It's the angle from the optic axis to a particular maxima, right? That would be the m equals 1. The next one would be the m equals 2. Next one would be the m equals 3, and so forth. So if I go to a higher wavelength, does theta get bigger or smaller? Bigger, right? Bigger over here means bigger over here because sine of theta increases all the way up to theta of 90 degrees. So red is in fact going to have an overlap with the central maximum, but then the next one is going to be pushed out a little bit. Okay, and so the red pattern is in fact going to look like this. All right, so why don't we label these angles as the following. This one we're going to call theta for the blue pen, and this one we will call theta for the red pen. Now, clearly they don't line up right there the way we drew them. Clearly the second one doesn't look like it lines up either. So we need to figure out where they are going to line up. And if they're going to line up, then that means that we have the following. They line up when theta r equals theta blue. Okay? When those two angles, in fact, line up somewhere, then they are going to overlap the bright fringes up there. All right. If theta r equals theta b, then sine of theta r has to equal sine of theta b. But if I look at this equation, I know exactly what sine of theta is. Sine of theta is going to be m lambda divided by d. This one is going to be m lambda divided by d. But now I have to be a little bit careful, right? I have to be careful because this m is not necessarily the same as that m. This is m for red. This is m for blue. Okay. Lambda on this side is lambda for red. Lambda on this side is lambda for blue. So that equation, in fact, becomes this relationship between the two of them. And now we can probably figure out how to do this. MB over M red is going to be what? Well, I divided by the M red. The D's are going to cancel out on either side. And so I get lambda red over lambda blue. And lambda red over lambda blue is 900 over 750. And if you punch in 900 over 750 into your calculator, tell me what you get. What'd you get? 1.2. Okay, so the ratio of these m's is going to be 1.2. But m has to be an integer, right? That has to be some integer. So if I start with m equals 1, I could have m equals 1 or 2 on top. That's not going to do it. if I go m equals 2, then I could do 2 or 3 on top. That's still not going to do it. Okay, and so you just need to express this in terms of a fraction of integers. And you probably know what the answer is. mb over mr has to be what? 6 over 5. Okay? The sixth fringe of the blue pattern is going to overlap with the fifth fringe of the red pattern. Okay? So those are the relevant numbers. And the question was, at what distance from the central maximum on the screen will a bright fringe from one pattern first coincide with a bright fringe from the other? And so now that you know one of these, you can just pick the height here, ym, and now we just need to do a little bit of trig to figure out what that corresponds to. All right, so let's pick the theta r, which corresponds to the m equals 5 pattern. Okay. In the problem, they told us d. They also told us l. And so what we can say is d sine theta equals m lambda, but sine of theta in the small angle approximation is approximately ym over L. And so that equation becomes d times ym over L equals m lambda. And now we can solve for ym. Y sub m is equal to m lambda L all over d. And now we have all those numbers. We know that m for the red one is 5. We know that lambda for the red one is 900 nanometers. We know L, they gave that to us. L was 2 meters. And then D, they also gave us D. D was 2 millimeters, which is 2 times 10 to the minus 3 meters. And so we can put that down here, 2 times 10 to the minus 3. And now I don't even think we need a calculator for this, right? We've got 5 times 9 times 10 to the minus 7, and then we've got a 2, and then we've got a 2 times a 10 to the minus 3. The 2's cancel out. 5 times 9 is 45. And then we have 10 to the minus 7, and we have a 10 to the minus 3, so I need to add 3, so I get 10 to the minus 4. So that is, of course, in meters, but all the answers are in millimeters. And 45 times 10 to the minus 4 is the same as 4.5 times 10 to the minus 3, which is 4.5 millimeters. And if you look at the answers, answer D is, in fact, 4.5 millimeters. Questions on that one? You guys like the multicolor approach here? Give it a little flavor, yeah? Keeps me entertained back here. Okay, let's continue. So number 6 says a beam of monochromatic light passes through a slit that is 11 microns wide. If the first order dark fringe of the resulting diffraction pattern is at an angle of 4.31 degrees away from the center line, what is the wavelength of light? Okay, so this is back to a single slit problem. And the idea is this: we have a single slit, some plane wave coming in, creates this diffraction pattern. And we know that, we know the slit width. I think we were calling it, what were we calling it, D? Okay. I think I called it W in lecture, but that's fine, we can use D. And then they tell us that D is 11 microns, which is 11 times 10 to the minus 6 meters. And they tell us the angle to the first dark fringe. Okay, so here's the center line, and they tell us this angle right here. And that theta is equal to 4.31 degrees. All right, they are looking for lambda. So how do we do this? Somebody give me some thoughts. Jessica, what should we do?
Use the d sine theta equals m times lambda.
Okay. D sine theta equals m times lambda. So where did that come from?
Just the equation that we gave us.
Okay.
But we can solve it for lambda, can't we?
Okay. But this equation that you just told me, that was for the bright fringe from a double slit, right? And now we have the dark fringe from a single slit. So is this equation the same, or is it something else? Anybody have a thought? How do you deal with this? Let's say you're in the exam tomorrow. What are you going to do?
Use the same.
You're going to use the same equation and just hope? No, you're not. You're going to go to the formula sheet that I posted online for you guys, and you're going to look at that formula sheet and see if that equation is right or not. So let's pull up the formula sheet off of Blackboard and take a look at what it says. Okay, so you scroll down a little bit on the formula sheet, and we see the bright fringes from Young's double slit certainly obeys that equation, d sine theta equals m lambda. And if you scroll down a little bit more, hopefully, won't let me scroll down. There we go. We get to single slit diffraction, which says the dark fringe is a sine theta equals p lambda. That is, in fact, the same equation as this. Okay, in that equation, A is the width, and so that's D, and P is an integer, that's our M. So this is kind of weird, right? But this is the bright fringe for a double slit. It's also the dark fringe for a single slit. All right, good. So if we have that equation, then we might have everything we need, right? Because Jessica said, well, let's just solve this for lambda. That's what we're looking for. Lambda equals d sine theta divided by m. We have d. D is 11 microns, so that's 11 times 10 to the minus 6. We have the angle, 4.13 degrees, so we can take the sine of 4.13 or 4.31 degrees. And then we have m for this case because in the problem they say it's the first dark fringe. So m is in fact equal to 1 here. All right, punch in all these numbers into your calculator and tell me what you get.
(8.26 times 10 to the negative 7).
8.26 times 10 to the negative 7, and the units are, of course, meters. And if we look at the answers, all the answers say nanometers, so we need to convert this to nanometers. And if I move this over 2, then I have to subtract 2 from the exponent, and 10 to the minus 9 is a nanometer. So was there something after the 6? So this is 826 nanometers. And if you look at the answers, the closest one is answer A, 827 nanometers. Okay, so there's probably something else after that, but that's all right. All right, questions about that one? Everybody okay with that? All right. Okay, let's skip number 7. This is just more diffraction problems. I think we've done enough of those for right now. Why don't we jump ahead a little bit and look at the one that was suggested online, which is number 10. Okay, and number 10 is a question about a camera. It says the focal length of the lens of a simple film camera is 40 millimeters. By what amount should the distance between the lens and the film be increased or decreased to change the focus from a person who is 25 meters from the lens to one who is 4 meters from the lens? Okay, so this is a camera problem. And let's just draw a simple picture of our system. Okay, here's the lens in the camera. Here is the film plane. And there is an object that is 25 meters away. Okay, so for the first part we have 25 meters. And you can follow your simple lens rules to figure out where the image is. I guess we usually draw those with solid lines, right? So we'll keep them solid. And therefore the image is right there. Now, they tell us that the focal length of the lens in the camera is 40 millimeters. Okay. This distance here is the image distance. So with those two numbers, we should be able to figure out the image distance in this first case. Why don't we do that? 1 over f equals 1 over do plus 1 over di. So let's solve this for di. We've got 1 over di equals 1 over f minus 1 over do, or di equals 1 over that whole thing. Okay, and somebody punch in your calculator what these numbers are, and let's just calculate di to start. So 1 over f, we've got 1 over 40 millimeters. Put everything in meters, so that's 0.04. And then DO is 25 centimeters. That's a minus, sorry. So we have minus 1 over 0.25. And if you punch in those numbers, tell me what you get for DI. And I can tell you it's got to be pretty close to 40 millimeters. Certainly going to be bigger than 40 millimeters, but it should be in that range.
$0.01.
0.01?
I might have added a 0 in there.
That doesn't sound quite right to me. Because this is going to be like 20, and this is 4, right? So we're going to get 20 minus 4, so that's about 16. So 1 over 16 should be 0.1. Anybody get an answer for that one?
$0.0.
0.047? That sounds right. Okay, and that's in meters. That's certainly bigger than F, but not much bigger than F. Okay, that sounds right. Okay, so now we're going to take the object and we're going to move it much closer. DO is now going to be 4 meters. And we need to figure out what this image distance is going to be in this case. Okay. And what stays the same, of course, is the focal length of the lens. So if we had left the lens exactly where it was, and I brought that object in, would the image move closer to the focus or further away from the focus? It would, in fact, move further away from the focus. Okay, so you still follow your lens rules, but the image would be out here. And so, in fact, I need to move that lens further away from the film. But since they give us all those numbers, we can just calculate it, right? We know DI in this case. DI is going to be this thing, 1 over F minus 1 over DO. But we have new numbers for DO. So we have 1 over 0.04 minus 1 over I think we messed this up, didn't we?
Yeah, it's 25.
Yeah, that's, I thought that was centimeters. That's not centimeters, that's meters. This was not 0.25, this was 25. In which case, this number is going to be basically 0.4. Double check me on that one. There might be one more digit after it, but it's basically 0.04. Okay, and now if you do this, tell me what you get. This is good practice for tomorrow, punching things into your calculator. Anybody else bring their calculator with them?
We got .04.
For the first one,
No, for the second one.
you got 0.04, 0.0404, and what'd you get on the first one?
0.040064.
Okay. So if I take the difference between those two, what do I get? Something really small, right? It's going to be that. So delta of di is going to be 0.0404 minus 0.04006. And if I do that, what do I get? I get 0.0004, right? That's 4 digits, and that's 4 digits. So something on that order, meters. Okay, is that one of the possible answers? Yeah, it is. That's 0.4 millimeters, which is answer D on there. Okay. So in fact, this is important to keep all these digits because those two are very close to each other. And this is kind of a neat idea, right? If I have a camera and I want to look at something very far away, 25 meters, I set it up. But now when that object's only 4 meters away, I only have to change that lens position by a fraction of a millimeter, a half a millimeter. Okay? And you know this already because in your smartphone camera, you can basically see from infinity all the way into something very, very close, right? You can take a picture of yourself when you do a selfie, no problem. That camera lens can't move very far because your smartphone is very thin. Okay, so this is confirmation of that. All right, why don't we take a 5-minute break and I will see you guys back here and we'll try a few more of these. Okay. Hi guys, welcome back. We just finished working out number 10. I think we came up with 0.4, but double check all the digits in that calculation because I think the correct answer was actually 0.3. So keep all the digits in your calculator. Let's take a look at the next one, number 11. And this is the problem with Alice being farsighted, and she can't see objects that are closer to her eye than 80 centimeters. What is the refractive power of the contact lenses that will enable her to comfortably see objects at a distance of 25 centimeters from her eye? Okay, so this is a contact lens problem. And remember, a contact lens is just another lens that you put right in front of your eye. So let's draw the issue here. Here's her eyeball, and she can see things that are 80 centimeters away, no problem. Okay, which means that she can focus that image onto her retina. But when that object comes in a lot closer to 25 centimeters, now she can't focus it on her retina anymore. It, in fact, is going to focus behind her eyeball. Okay? So this is, of course, somebody that is what? Farsighted or nearsighted? Farsighted. Alice is farsighted because she can see things that are far away, but she can't see things that are close. So right off the bat, if you're going to fix Alice's eyeballs to read, do you want to use positive lenses or negative lenses? Yeah, you need to use a positive lens in this case. Reading glasses are positive lenses. All right, so we're going to take this picture now and we're going to add a positive lens. So here's her eyeball. I'm going to put a contact lens right on her eyeball, and now the image is formed on the retina. So when you put two lenses together, do you add their focal lengths? If I have f1 and f2, is the resulting focal length going to be f1 plus f2? No. That doesn't sound right, because that would be a much longer focal length lens. And I know that if I put a magnifying glass next to my eyeball, right, it's going to act like a shorter focal length lens. So when you add two lenses, you in fact add their powers. And power is 1 over the focal length. And remember, the units are 1 over meters, which is diopters. So in this new case, we need to figure out how much power to add in a contact lens. And to do that, we need to know the power of her eyeball in the first case. Okay? Okay, so what is the image distance? The image distance is the size of the eyeball, which is 25 millimeters. And therefore, in this case, we have 1 over f, bless you, equals 1 over do plus 1 over di. And this is, we'll call this f of her bare eyeball. DO is 80 centimeters, so that's 1 over 0.8 meters. DI is 25 millimeters, which is 0.025 meters. And if you calculate this, you are in fact calculating the power of the bare eyeball. And what do you get if you do that? You can almost ignore the 1 over 0.8. This is going to be a much bigger number, but punch it into your calculator anyway and tell me what you get for the power of her bare eyeball. No, because this is going to be something like 40, right? And this is going to add another 1.2 to it. So I'm going to say that you should get somewhere around there. Anybody get that in their calculator? 41.2? Okay. So 41.2 is the power of her bare eyeball. But now we're going to add a lens to the system right in front of her eyeball. And we have a new DO. DO is now 25 centimeters. We have the same DI because it's the size of the eyeball, 25 millimeters. And so now we can calculate the power of the contact plus bare eyeball system. And that is going to be 1 over f of the contact plus bare eyeball system. And that is 1 over 0.25 plus 1 over 0.025. And what do we get if we do that? well, this is still 40, and this is 1/4, which is 4, so I'm going to say it's 44. Is that what you guys got? Okay, these are both diopters. So the bare eyeball was 41.2. The system together was 44. And since you can add powers, what is the power of the contact lens? It's just the difference. It's going to be the power of the contact with the bare eyeball minus the power of the bare eyeball. 44 minus 41.2, and that's going to equal 2.8 diopters. And that's a positive number. And if we look at the answers, one of them is really close to 2.8. It is answer B. It says 2.75. So there must have been a little bit of extra digits here somewhere that we missed. Okay, and that sounds like a reasonable number, right? When you go to get your prescription, what does it say? It says plus 2.8 or plus 3.5 or -3 or -2. Okay, that's the power that you're adding with this contact lens. Yeah.
Someone asked, where did you get the .025?
That is right here, the size of your eyeball. Okay.
There were some questions.
So we talked about that in class. Hopefully that you guys remember that that's the size of a human eyeball, the average human eyeball.
And for question 10, someone said that when they did it, they got 3 and not 4, so they believe they answered A.
Okay. So hopefully that question came before we just said that the answer should have been 0.3, not 0.4, and it is answer A. But that could have been part of this delay, right? Because there's a 52-second delay, apparently, between what I'm saying and what people are at home are hearing. For the rest of you, it's probably more like 10-second delay, right? No? Your coffee's kicked in? You guys are ready to go? Okay, so let's look at number 12. This is the microscope question. And this one says the following. A compound microscope has an 18-centimeter long barrel and an objective lens with a focal length of 8 millimeters. What's the focal length of the eyepiece to give a total magnification of 240? It's adjusted for minimum eye strain for persons with a near point of 25 centimeters. Okay, magnification of a microscope. Anybody remember what we came up with for that? It's okay if you didn't. L times 25 centimeters. Okay, that's right. And I think maybe there's a minus sign to say it's inverted, right? But we don't really care about whether the image is inverted or not. So it's that. It's L times 25 centimeters over the focal length of the objective times the focal length of the eyepiece. So if we're going to keep everything in SI units, then this should be 0.25 over the focal length of the eyepiece times the focal length of the objective. And they give us a lot of this information, right? L is the length of the barrel. So here's your lens, here's your other lens. This is L. That's your objective, that's your eyepiece. You put your little bug down there, and you take an image of it. Okay? And how big that bug looks to you is given by the magnification M times the original size. So, how do we do this? Well, they tell us M, right? M is 240. They tell us L, 18 centimeters, so that's 0.18 meters. And they also tell us the focal length of the objective. Focal length of the objective is 8 millimeters, which is 0.008 meters. And we need to calculate the eyepiece. All right, so it's not too bad because we know everything in this equation except the eyepiece. And so let's just solve this equation for the eyepiece. F of the eyepiece, and just ignore the negative sign, okay? We're just going to worry about the magnitude here, so we'll make that a positive. F of the eyepiece is going to be what? I got to multiply across by FE and then divide by M, so I just trade places with the FE and the M. So it becomes L times 0.25 divided by M times FO. And now I have all those numbers. 0.18 for L, 0.25 for the near point of the eye. That's where that 0.25 comes from. M is 240. FO was 0.008. And now if you punch all that into your calculator, tell me what you get. What'd you get? 2.3?
Yeah, centimeters.
2.3, so 2.3 times 10 to the minus 2 meters, which is 2.3 centimeters. Yeah? Okay, and that is in fact one of the answers. Did anybody else get 2.3? Do we have verification on that?
Yeah.
Okay, good. Okay, any questions about this? No? Okay. All right, let's take a look at (13) is sort of a short answer. Let's skip that one. 14, we talked about in class. We just talked about a lot of these problems in class. So let's just skip to two of the last ones. Let's go to number 17.
Someone also wanted you to do 16.
Okay. I don't know if I want to do 16 here, though. So send them a message back saying, we might not get to it. Let's take a look at 17 first. So 17 says, astronaut Hans leaves the Earth in a spaceship traveling at a speed of 0.28 c relative to the observer Brian at rest on Earth. Hans is holding a pencil at an angle of 30 degrees with the direction of travel as seen by Hans. What angle does the pencil make with the direction of travel as seen by Brian on Earth? All right, this sounds like a good, difficult problem. So let's see if we can visualize what's going on here. Okay, here's Brian standing here on Earth, and he's observing Hans flying by in a spaceship. So here is our spaceship, and Hans is standing in there, and he's holding a pencil, and that pencil is making an angle of 30 degrees relative to the direction of travel. Okay. And the whole spaceship is moving along at speed v, which is 0.28 c. And the question is, what angle does the pencil make according to Brian? Okay. So it's kind of a weird question, right? I mean, this astronaut's flying by and he's holding a pencil up at some angle. It almost seems like this guy should see the pencil at the exact same angle. But that's too obvious an answer, right? And in fact, we're not going to be suckered into answering A, 30 degrees. So what is really going on here? This is a little bit related to what we said yesterday in class when we talked about length contraction. Okay. Length contraction is the following. In the moving frame, if you measure L naught by the guy in the spaceship, then L as measured on Earth is going to be shorter. Okay? This number is smaller than 1, so this is going to be L naught as measured in the spaceship. This is as measured on Earth. Okay, in this case, that would be Brian. Brian's the one that stayed on Earth. L naught is the measurement in the spaceship. So that's measured by Hans. Okay, but they're not asking about the length of the pencil. They're asking about the angle that it makes relative to this horizontal axis. What can we say? What we said in class yesterday was, imagine you have a box, and that box has height h naught and length L naught. And now you take that box and you start moving it at some fast speed, v. Does the height of the box change? No. The length changes. This length contraction is only in the direction of motion. Okay, so the box shrinks in that direction. So by analogy here, this pencil that is angled looks kind of like a triangle. Here's our pencil. Okay, but there is a horizontal component and there is a vertical component. And that horizontal component, let's call it L naught. And the vertical component, let's call it H naught. And this thing, let's call it theta naught. But when it starts moving and Brian takes a measurement of it, L naught shrinks. H naught stays exactly the same. And so in fact, the pencil looks like it is more upright. And let's call that angle theta. H naught stays the same, but the L shrinks. All right. What is the tangent of theta naught? The tangent of theta naught is H naught over L naught. What's the tangent of theta? Tangent of theta is H naught over L. But H naught over L is the same as H naught over the square root 1 minus V squared over C squared, all of that times L naught. And H naught over L naught, we know what that is. That's just the tangent of theta naught. And so now you can put all this stuff together. And so we have the following. Tangent of theta equals H naught over L naught, 1 over square root 1 minus V squared over C squared. But that is 1 over the square root 1 minus V squared over C squared times the tangent of theta naught. And now you know all of that stuff. You know V, you know theta naught, you can calculate theta. So let's plug in some numbers and see what we get. We've got 1 over the square root, 1 minus 0.28. That thing is squared. The c's are, of course, going to cancel out. And then we have the tangent of 30 degrees. And we're going to take the arctangent of that whole thing. And that's going to be our theta. Okay, a few of those answers don't make any sense at all. 30 degrees, that doesn't make any sense because we know the angle is going to change. 29 degrees doesn't make any sense because we know that it's going to get steeper. So the other options are 31 degrees, 33 degrees, and 90 degrees. But 90 degrees, it would be standing straight up, and that means that the bottom side of that triangle would have to shrink to 0, which would happen when you're going at the speed of light. So we're not going at the speed of light. So really we're down to two options, 33 degrees or 31 degrees. Did anybody punch it in and get an answer for this? 31 degrees. Okay, and that's answer D on your answer key. All right, so that's a good, challenging problem. Let's do one more easy one, and then I think we're going to finish up for today. All right, let's just do the last one, number 18. So a star is moving toward Earth. And it's moving at a speed of 90% the speed of light. The star emits light, which moves away from the star at the speed of light. What do Earth-based astronomers measure for the speed of this light? So here's the star spitting out light in all directions, also moving toward us. here on Earth. Okay, the star is moving at v. It's emitting light in all directions. If you're on Earth and you measure the speed of that light coming towards you, what do you measure? C. What if the star was moving away from us at 0.9 c? What would you measure on the Earth for the speed of light? C. Okay. This is the second postulate of the special theory of relativity. No matter what the source is doing or what the observer is doing, you're always going to measure the exact same speed of light, c, which is one of the answers, answer E. Okay, key for this will show up later today. I'll post the clicker questions later today. The few that we haven't got to, try to work out with your study group. And I will see you guys tomorrow. Cheers.